Welcome to Stochastic Processes Lesson 6a. The reason I'm calling it 6a, it's an optional lesson and it involves the generating function for the first return uh, to state zero that we talked about in the previous lesson, and I just gave you the generating function without deriving it. So it's not all that easy. This is probably one of the longer lessons in the group, but you could skip it without losing continuity and just go on to the following lesson if you wish. But if you're interested in how generating functions are developed, then you may want to have a listen to this lesson. So just as a reminder where we left off, in part 6, the previous lesson, we wanted the first return probabilities of the symmetric walk. In other words, a walk where the probability is 1/2 going left to right. And I gave you the answer here. And then we wrote this as a Taylor series, and we were able to read off the coefficients, which gave us the first return probabilities. And at the time I mentioned that finding this was rather difficult. And initially I said I would refer you to my book, which in turn pointed to another book that had the uh, explanation or derivation of this. And then I changed my mind and I decided to actually show how this is derived. So that's what we're going to do in this lesson here. The plan is two relationship. We're going to find two relations between two generating functions, and then we'll solve those. That'll be towards the end of the lesson. Uh, and the only ingredient is a counting argument, which is a little bit complex, but we'll prove that also. This slide is a summary of where we're at. Previously, we found the probability of returning to state zero, given that you were in state zero to start with, in 2n steps. And we computed that to be this quantity here. 2n choose n times 1 over 2 to the n. So this is the probability of being in state zero, given that you started at state zero after 2n steps. And then we derived this in the previous lesson, the probability of the first return to state zero at step 2n. However, as I mentioned in the previous slide, and also in the last video, I gave you the generating function, which allowed for us to read off the coefficients of the Taylor series for the generating function, which were the probabilities we seek, but I didn't show how to find the generating function. So that's what we're going to do here. We derived this formula in the previous lesson, so let's just quickly review that because we need it again. It's using the law of total probability, and it's saying the probability of starting in state zero and returning into state zero at step 2m is the same as the probability of having your first return to state zero in 2 steps and then coming back to state zero in 2m minus 2 steps, or having your first return to state zero in 4 steps and returning back to zero in 2m minus 4 steps, and so on. Basically, all the different possibilities of the first return being 2, 4, 6, 8, and so on steps. So that's what this is here. And if you recall, the issue I mentioned is that what we're really looking for is this probability here, f 2I, but it's embedded in this formula. And the way to extract that is to define a generating function. So now we're going to actually derive that, but we need more than just this formula. So we'll see that as we proceed. I have a few points here. Let me see if I caught them all. Every term is a product of one f and one p. Yeah, I think I've said that. That shape is a convolution, and convolutions are what generating functions are built for. So we'll get to that. And then the restriction are m greater than or equal to 1. So we also have the case where the p sub 0 equals 1. We'll need to take that into account. That's sort of when you just start. You're of course in state zero when you start. So let's continue. We have two functions that we've defined earlier, but I want to emphasize them here since we need the notation and to make use of these. So this P of S is a sum, an infinite sum, and the coefficients are the probabilities of starting in state 0 and returning to and being in state 0 at time 2n. In other words, after 2n steps. And then in a similar way, we have this series here, and it's the coefficients or the probability that the first return to state 0, given that you started at state 0 at step 2n, and that's these f sub 2n's. So what we want to do is find two equations involving p and f, and we'll solve those, and the solution to that will give us the generating function for f of s, which is what we want, and then what we were given in the previous lesson, but now we're going to actually derive it. And then one small point, which I mentioned on the previous slide, we need in order to capture this properly, we want to split off the P0 term, and then you just have the rest of this from, I changed the subscript, but it's the same idea, from n equals 1 to infinity of this. Okay, and then one other point, I believe I called this G of S on the previous lesson, so not to confuse you, it's the same thing. I went with F here because I think it's easier to remember. This is the first return probabilities, and these are just the probabilities of being in the state after so many steps. So this is kind of more of an easy way to remember these two. Okay, so on the next slide, we'll finally start getting into the solution to the problem. So let's continue with our analysis. 2 slides back, we derived this formula here. And in fact, we derived that earlier in the first lesson. We want to make use of this. At the bottom of the last slide, we had a formula for P of S. It was 1 plus summation from m equals 1 to infinity of P sub 2m times S to the 2m power. And then we're going to substitute in this summation for P2m, which is what I've done here. And what I want to do to this double summation is to shift the order and then separate the terms. So that'll take a little bit of effort. The first thing to mention is this goes from m equals 1 to infinity, I equals 1 to m. So for each value of m, you have a set of values for I. So this is m equals 1, m equals 2, you get 2 different values for I. M equals 3, you would have 3 values for I, and so on. So these are the points I, m from this summation here. And I want to map this to a different set. They're going to be at least represented differently, same set, but represented differently. And that'll be the set ij. So we're keeping I as before, but j is now defined as m minus I. And my claim is these points are the same as these points here. So this first point down here, where j is 0 and I is 1, so that's this 1, 0, is the same as this point here. You notice when you, m is I plus j, so this is, when you add these together, you get 1 for m. And then this point here is 1, 1. It's I equals 1 and j equals 1. And m would be 2. So we've moved up to this point here. And then the next one is I is 2 and j is 0. So that's this point. And in that case, again, m would be 2 and I would be 2. So that's here. If you go to the next set of points here. It's this point here, and then this is 3, 0, and those are the 3 points here. So basically we've, if you take this and you kind of shift it, and you can see that it's the same as these here. So this is the first, this is the second row here, going diagonally. This is the third. And if I have it right, this, maybe I should draw on it. Not that. Then these points would be the fourth, like that. Okay, so the point is they're the same set of points, and we've changed this now to a summation over ij, where I is greater than or equal to 1, and j is greater than or equal to 0. And then we change the order of summation, as I've shown down here. So I've just subtracted the 1 from this side here, and then I've substituted in j for m, and I've changed the order of summation. And we also needed to make the substitutions into the formulas here. So we had I remained as it was, so we have f sub 2i, f sub 2i here. But then this here, 2m minus 2i, 2m minus 2i is just 2j, so that becomes 2j. And then this m here, if you solve for m in terms of I and j, it's m equals I plus j, and so you get 2 times I plus j. So that's the transformation of this into this. And you may be questioning why I was able to switch the order of the summations, because that doesn't always work. And it's safe to do here because the two power series are equal when their coefficients agree. And the coefficients of s to the 2m is the same finite set of m terms before and after the substitution. In fact, it's this here. So if you took the coefficients for s to the 2m, you're just going from I equals 1 to m, and you get this set from here. And if you do the same thing here over all the terms for s to the 2m, where m is equal to I plus j, so in other words, I plus j equals m. If you do that over the same set of terms, you will also get this here. Okay, so that might be a little bit hard to take in while I'm talking through it, but I'll leave it for you if you want to double check. But again, the coefficients for 2 to the m are the same in this case and the same in this case here, which is why the switching of the summation is valid. But this gives us something really useful, which I'll show you on the next slide. I took the formula from the previous slide and I put it here at the top, and I broke up the s to the, was s to the 2i plus j, and I wrote it as s to the 2i plus 2j. And you notice that we have this term here, f sub 2i and s to the 2i, neither of which have a j in it. So we can move those out of this summation, which I've done here. And then what's left are just the terms that have a j. And so now we have the product of two summations. And this first one was f of s, we defined that earlier. And the second one is p of s, we defined that earlier also. So now if we take the 1 to the other side, we have p equals 1 plus pf. Okay, so that's one equation. Now we want to find f, and since we have two unknowns here, p and f, we need a second equation with two unknowns, and then we can use those two equations in order to solve for f. So that's what we're going to get to in the remainder of this lesson. If you want to check this, we can do that. We can on this side here, we can use our formula from slide 2 to compute p sub 2 and p sub 4, which I show up here. We knew that p sub 0 is 1. So we have that here. Then on this side, we can check for the coefficients of s sub s raised to the 2 power and s raised to the 4 power. And the coefficient of s to the 2 power is p sub 0 times f sub 2. And then the coefficient of s to the 4th power is p sub 0 f sub 4 plus p sub 2 times f sub 2. We already computed, we already know p sub 0, and we computed p sub 2. F sub 2 and f sub 4 we can compute directly. F sub 2 is the first return. There's only 4 ways of taking 2 steps. Either you can take 1 step to the right and then back, or 1 step to the left and back, or you could take 2 steps right and 2 steps left. So out of those 4 possibilities, only 2 of them bring you back to 0, so the probability is 1/2. Then in the case where you take 4 steps, there's only 2 ways of coming back, but there's 16 ways of taking those 4 steps. And so this probability is 1/8. And you just plug these numbers into these formulas, and you get 1/2, and that checks out, and you get 3/8, and that checks out. So we can solve for f in terms of p from the equation we derived on the previous slide. And I've done that here. But this is not enough because we need to know exactly what p is. And that's the next task for us to do. We need to find another equation, and then we can plug p in here in terms of f and then solve for f. And the second relation, which we're going to develop, comes from a fact about the walk itself and not about algebra. So we'll see that on the next slide, or at least starting on the next slide. We have a second relation, which we're going to need to prove. I'm just stating it here, saying the probability of the first return to state 0, given that you started at state 0 at step 2n, is equal to the probability of being in state 0 at step 2n minus 2 minus the probability of being in state 0 at step 2n. We can check that out using the probabilities that we've computed before. So if we look at, we can check out a few of them, not all of them, obviously. So we have P0 minus P2, and that's 1 minus 1/2. That's equal to 1/2, and that is, in fact, F2. And then we have P2 minus P4, that's 1/2 minus 3/8, and that equals 1/8, which in fact is F4. If you recall, we just computed some of these inputs on the previous slide, so they check out. So that gives us some confidence to go ahead and see if we can prove this in general. Let's continue. On this slide, I have an identity, which we're going to need to prove. But what I want to show first is this identity gives us our result from the previous page, that f sub 2n equals p sub 2n minus 2 minus p sub 2n. So it's rather unusual and unexpected. It's saying the probability of starting in state 0 but not returning to state 0 in step 1, 2, 3, all the way up and including 2n, that equals the probability of being in state n at 2n. So 2 quite different events, but they actually are equal in terms of the probability. Again, we'll have to show that. But what I want to show here is how this, if this is true, how it gives us our identity from the previous slide. So to set this up, we define 2 events. A, the walk avoids 0 through step 2n minus 2. And B, the walk avoids 0 through step 2n. So B lies inside A. Avoiding 0 for longer is a harder thing to do, so I've shown it here. B is more restrictive. right? In order to avoid 0 for 2n steps is more restrictive than avoiding 0 for 2n minus 2 steps. So B is in A. A but not B, that's this orange thing here. It's, in other words, you're clean or you don't return to state 0 through step 2n minus 2, and then hit 0 at step 2n minus 1 or 2n. Odd returns are impossible. We've seen that was the parity principle. So we hit it at step 2n. That is the first return to 2n. So A, the outer circle here in the Venn diagram, A splits into two pieces that do not overlap. B inside here, and then A but not B, which is the orange. And so we have the probability of A equals the probability of B plus the probability of A not B. That's just saying this outer probability is equal to B plus the orange, which is A not B. And so we have this here. But probability A not B is basically the probability of returning to 0 for the first time at step 2n. And that's this F2n. So F2n equals this here, which I've written out. And then this one here, assuming this is true, which we have to prove, this is Pn, P sub n 2n minus 2 minus P sub 2n. Okay, so if this is true, then our result from the previous slide is true. So we've reduced our task to showing this, which I agree is quite unusual, but we're able to prove this on the next few slides. So let's look at that. Counting the paths that avoid 0. So let's continue. Each of the 2 to the 2n paths is equally likely. So this is a counting problem. We first use symmetry. And you notice here we're just looking at the case where all of them are at each step were greater than 0. And then we can just multiply by 2. So we're working with this case here. A path avoiding 0 stays entirely above it or entirely below it, and the two cases mirror each other, which is just another way of what I just said here. We're going to look at something called the reflection principle. A positive path opens with a step up to +1, showing that here, so that what we want is the number of paths from 1 to 2r and the remaining 2 minus n steps. So this was the first step, and then you have 2n minus 1 steps remaining. We get that by counting all the paths and then subtracting the paths that do touch 0. So the hard part is figuring out what exactly are those. And we can use this reflection principle to figure out what they are. Call a path bad if it touches 0, since those are the ones to exclude. Find the first step where a bad path reaches 0. So that, for example, I have this here as a bad path that I'm outlining. So this is where the first time it hits 0. Flip everything before that point about the line at height 0. In other words, this line here. So we flip this down here, the dashed line, and leave the rest of the path alone. So now we have this path here. So the opening +1 now becomes -1. The first touch of 0 is its own mirror image, in other words here, and the path still ends at 2r. So every bad path turns into a path running from -1 to 2r. And that's the key. So we count all the paths from 1 to 2r over the range of possible values for r, and that including the ones that hit 0. That's the total number. That's a combinatorial problem. And then we count, and in 2n minus 1 steps. And then we count all the paths going from -1 to 2r in 2n minus 1 steps that hit 0. In other words, all the bad paths. And we can do that by counting these this way. So that's yet another combinatorial problem. And we'll do those two problems on the next slide. We'll subtract them, and then we'll multiply by 2, and then we'll get our probability we're looking for here. Counting the two families. So let's compute the number of good paths based on what we discussed on the previous slide. A positive path opens with an up step to state 1, as we showed previously. So we count the paths of length 2 and minus 1 from height 1 to height 2r, with r being between 1 and n. And we're going to write u for the number of up steps and d for the number of down steps. So first we'll compute all the steps, all the paths, going from 1 to 2r, and then we'll compute just the bad paths that end up in 2r but touch 0. So the total number of up and down steps is 2n minus 1. And if we subtract the number of down steps from the number of up steps and add the initial starting point 1, that should be 2r. We solve these two equations for d and u. We get this here. I'll leave it for you to check. And then the total number of paths from 1 to 2r is the total number of ways of selecting the n minus r down steps out of the 2 n minus 1 total steps. That's this here, and that gives us this number here. And then computing the number of bad steps given the reflection principle from the previous slide is almost the same. It's just that you start at minus 1 and you want to end up at 2r. So the total number of steps is 2n minus 1 as before. However, instead of adding 1, you need to subtract 1 and still get to 2r. You solve this and you get these two results. And then the total number of bad paths is the total number of ways of selecting n minus r minus 1 down steps out of 2 n minus 1 total steps. And that gives you this here. And then you just subtract this from this to get the total number of good paths. But we need the sum from r equals 1 to n. So we'll do that on the next slide. The sum telescopes. So we have the result from the last slide here. And as I mentioned, we need the sum from r equals 1 to n. So we'll sum here on this one. And then we'll sum from r equals 1 to n minus 1 in this case here, since we don't want to get a negative in the lower part of the combination. So we stop at n minus 1. Then we do a change of indices. We let j equal n minus r. So you notice j is here. Then these things, the summation kind of goes in reverse. In other words, when r equals 1, j equals n minus 1. And when r equals n, j equals 0. That's why, so that could potentially be a little confusing that you're flipping the order. But you get this is equivalent to this. And then you make another change of indices here. You let j equal n minus r minus 1. So you get a j here. And you have the same inversion that I mentioned here. This sums up to n minus 2. But the nice part is you have the same summand in here, the same thing that's being summed, whatever this is called. Maybe it's not the summand, but whatever this is called, it's the same. And you know, this goes from 0 to n minus 1. This goes from 0 to n minus 2. So everything cancels except for the j equals n minus 1. In other words, this here. So we get a huge amount of cancellation. And that's our final result when we sum over r. So we're almost there, a little bit more to do. We computed the total number of paths that remained above 0, but we want the total number of paths that don't cross or return to 0, don't cross 0. So we need to multiply by 2. That's what I've done here. So I just took the result from the last slide, multiply by 2. If you do a little bit of algebra, you can show that this is equivalent to this. Now we want to know the probability of no returns. So we take the total number of paths given 2n steps, that's this number here, and this is the total number of paths that do not return to 0 in 2n steps. And so we just replace this with this, and we get this here, and this is in fact our formula for 2 of subscript 2n. In other words, the probability of returning to state 0 or being in state 0 after 2n steps. If you recall, I know it's quite a few slides back, we wanted to show that this probability is equal to this probability. And in fact, now we've finally done that. And if you recall from multiple slides back, and you may need to look at this a second time, I know there's a lot here. We said once we can prove this, then the result we really wanted, that the first return after 2n steps being equal to the probability of being in state 0 after 2n minus 2 steps minus the probability of being in 0 after 2n steps. These two things are equal. So now we have this shown, and we can complete the intent of this lesson to actually find or derive the generating function for these probabilities. So finally, we return to the generating function for f of s. This is by definition. Then going from here to here, we substituted in the formula we proved. So we just put that in for f sub 2n. Then we break this into two pieces. On this left side, you notice we have a 2n minus 2. So we want to match that up with the s power of s. So we'll just factor out an s squared. Now we have this form here. I have a little note on the bottom also. This is actually p of s, this term in here. Then this side is easier in the sense that we don't need to factor out any s, but the first term is missing from this. So this is really p of s minus 1. P sub 0 is 1. And I note that down here. And so following this all the way down, we have f of s equals 1 minus, so just factoring the ps out of here. So we get 1 minus s squared times ps. Okay, going from here to here is just a little bit of algebra. And so now we have this equation that we just derived here. And then we had the original equation from way back, much earlier in the lesson. And so now we have two equations and two unknowns, and we can solve those, which we'll do on the next slide. So as we saw in the last slide, we found two different expressions for f. 1 minus 1 over p, and also 1 minus s squared p. We can cancel the 1. Maybe I should draw on the slide. So the 1's cancel out. Then we multiply both sides by minus p, and that gives us a 1 on this side. And then this minus 1 becomes a plus 1, and this is p squared. We get this here. Then we just divide both sides by 1 minus s squared and take the square root on both sides. And we get this here. So p of s is 1 divided by 1 minus s squared. But what we were really looking for was f of s. And so we just plug this into here, 1 minus 1 over p. And then we just get 1 minus the square root of 1 minus s squared, which I called g of s, and that's why I wrote it here. I called it g of s in the previous lesson. And if you recall from the previous lesson, I just gave this as a given. And initially I referred you to a book, but then I changed my mind and decided to derive it, which is what we've been doing here. And you can see why I was kind of tempted to push it off. It's not an easy thing to derive. And then on the last lesson, the previous lesson, we expanded this in the Taylor series, and then we were able to read off the coefficients of the Taylor series to get the various first return probabilities. Okay, so that's pretty much it. I have a little bit of a summary on the next slide. Let's look at that. So using our formula, we can put in 1, f of 1. The probability of return is certain, setting s equal to 1. Adds up every first return probability. The total is 1. So the symmetric walk on the integers is certain to come home back to 0. In lesson 6, we quoted this result from the mathematician Polio, but here we've proven it. In the previous lesson, we mentioned how the part of the coefficients of the Taylor series for the generating function was the Catalan numbers. So I'm just kind of restating that here. This is just summarizing all we went through. We had to find two identities, both involving f of s. Then we set them to each other. We solved for p of s, and then we plugged that back into one of the two equations for f of s, and we got our formula for f of s, which was the whole point of this rather long lesson. Okay, so that's it. Lesson 7, we're going to go back to the classification of Markov chains, and then after that, I have yet another, at least plan to have another 5 lessons after lesson 7. So if you like this, please give it a thumbs up and stay tuned for additional videos.